Section 9.2 is all about special right triangles. Alright, and we're going to be talking particularly about two different types of special right triangles, and we define these triangles as being special by some angle measurements. So first off, they're going to be a right triangle, so you're going to have a 90-degree angle. And there's really two kind of special right triangles. The first one, which will be a theorem, and we'll label that one theorem 9.4, is going to be the 45 degree, 45 degree, 90 degree right triangle. Or in other terms, 45, 45, 90. You've probably heard me say that in class a couple of times. Now we're actually going to define our 45, 45, 90 right triangle. So we'll draw a picture of that. What's unique about a 45, 45, 90 right triangle is that it's actually, oops, my triangle would make, there we go, is that 45, 45, 90 right triangles are actually isosceles triangles. So both of these legs coming off of our right angle here are going to be the same distance x. And then our hypotenuse, the side that's opposite of the right angle, is going to be x times the square root of 2. So that angle up there is 45 degrees. This angle on the bottom right is 45 degrees. And a good way to view a 45, 45, 90 is if we were to take, say, like a square. It's close enough. And we cut that square in half. So when you cut a square in half diagonally, you get two 45, 45, 90 right triangles. And so just putting some verbiage on this in a 45, 45, 90 right triangle. The hypotenuse is the square root of 2 times longer than the leg. And the big thing to take away from this as well is that it's every 45, 45, 90 degree right triangle is an isosceles right triangle. Remember, an isosceles triangle is a triangle that has two legs that are congruent. They're the same length. So two congruent legs. All right, so with this bit of information, you can find some, or you can solve some triangles. All right, and when I say solve triangles, I mean find some missing legs, find some angle measurements, that sort of deal. So I want to find the value of x on both of these triangles. All right, the first triangle A is going to look something like so. All right, and you know, my drawings won't be perfect, so that's okay. But we can tell it's a 45, 45, 90 right triangle if we just know one of the angle measurements, right? If this angle right here is 45 degrees, then this angle over here has to be 45 degrees because a triangle has to add up to 180 degrees. And so if I say this leg over here coming off the right angle is a length of 8, I want to find the hypotenuse length, x. And since this is a 45 degree, 45 degree, 90 right triangle, then we know that the hypotenuse, the longest side, is equal to the square root of 2 multiplied by the length of one of the legs. So all we need to do now is substitute the leg being equal to 8 into our formula right here to solve for the length of the hypotenuse. So we're just going to take x is equal to the square root of 2 multiplied by 8, and that is going to be our answer. All right, we can't really simplify that. If you'd like to write this a little cleaner, we could write the 8 in front, so 8 root 2. There's no need to multiply it out. A lot of the time mathematicians will leave things as the square root of 2 because that's more specific, right? As soon as you start rounding, you can introduce some error. And error is okay, except when you need to be, very particular. All right, why don't I do a different triangle, except this one, we are going to know what what the hypotenuse is, and we're going to try to find the length of each of the legs. All right, that's close enough. That's a bad right triangle. We can, oh, what? My Notes app just crashed. That's unfortunate. There we go. Sorry about that, guys. All right, we good? All right, we're good. Draw my right isosceles triangle back in there. Close enough. We're going to signify that as a 45, 45, 90 because we know that each one of these legs is equal to a length of x. And so since it's an isosceles triangle, and since it's an isosceles right triangle, it must be a 45, 45, 90 right triangle. And because of that, then we know that the hypotenuse, which has a length of 5 times the square root of 2, we can solve for x based off of that information. So if the hypotenuse, once again, equals the square root of 2 multiplied by the leg, we can now solve this equation to find the leg. Because if we substitute all our numbers in here, well, we're going to have 5 root 2 is equal to x times the square root of 2. Right, and now you can see that each one of these has a square root of 2. And when we divide by the square root of 2 on both sides, the square root of 2 will cancel, and we're going to get x is just equal to 5. So it's pretty straightforward there. 45, 45, 90 triangles are really, really nice. So that's going to be our first special right triangle. Our second special right triangle is going to be called the 30, 60, 90 right triangle. That will also be a theorem, theorem 9.5. And so one of the angles will be 30 degrees, another one of the angles will be 60 degrees, and then finally, for it to be a right triangle, we must have our 90-degree angle. And so you've probably seen these quite a bit as well. They look like so. We have our right angle there. This larger angle on top is going to be 60 degrees. This skinnier angle down here is going to be 30 degrees. And we're going to have the shortest side here have a length of x. And so in a 30, 60, 90 right triangle, we know that the following pieces of information are true. The hypotenuse, so the longest side, is twice as long as the shortest side. So this length of the hypotenuse here, this longest side, is going to be twice the distance of the shorter leg. So it's just going to be 2 multiplied by x. And the longer leg is the square root of 3, kind of a weird number, times longer than the shorter leg. So our shorter leg is equal to x, then we know that the longer leg is going to be equal to x root 3. And so just to write this out, the hypotenuse is equal to 2 multiplied by the shorter leg. And the longer leg is going to be equal to the shorter leg multiplied by the square root of 3. And so now, just like we were doing before on these 45, 45, 90 triangles where we were solving for all the sides, we can do that same thing for 30, 60, 90 right triangles. And the reason why these are special right triangles is that we don't need the Pythagorean theorem to solve for all the sides. Because we know their angle measurements of 45, 45, 90 or 30, 60, 90, we can solve it using these really nice formulas. There's no squaring, there's no square roots, no Pythagorean theorem. So we're going to start, I'm going to go ahead and take these, put them down here below our gray line. These are going to be our formulas that we're going to use for our 30, 60, 90 right triangle. So these are for 30, 60, and 90 right triangles. All right, and we're going to find the value of x and y in this 30, 60, 90. Oops, we'll make that a right triangle. There we go. And so we're given that it's a 30, 60, 90, and the only side length that we're actually given is this longer leg. Just a second, let me look at my notes. All right, yep. This is the longer leg of 9, and then our short leg is going to be the x, and our hypotenuse is going to be y. And so we won't be able to find y here unless we know what x is, because we know that the hypotenuse, which is y, is 2 times the shorter leg. Well, we don't know the shorter leg because it's just an x. So let's first start by finding the value of x. And we're going to use the fact that the longer leg is equal to the shorter leg multiplied by root 3. And so now if we substitute in 9 for the longer leg, is equal to x, which is our value for the shorter leg, multiplied by the square root of 3, we can solve for that by saying, by dividing square root of 3 on both sides. And so x is going to be equal to 9 over root 3. Here's the thing about square roots. You never want to have a square root within the denominator. All right, it's just the way it is. It's like a standard nomenclature within mathematics. So we want to get this square root of 3, this radical, out from below our fraction. So to do that, we're to multiply the top and the bottom of this by the square root of 3, because the square root of 3 over the square root of 3 is like multiplying by the number 1. And so when we do that, right, this square root of 3 times this square root of 3 is just going to be equal to 3. So x is equal to 9 multiplied by root 3 divided by 3, or in other words, x is equal to 3 over root 3. All right, this is just a cleaner way to write the radicals. Once again, what we did there is we multiplied the top and the bottom of this fraction by the square root of 3, because that's like multiplying by the number 1. Instead of canceling this square root and this square root and getting the same fraction back, we multiplied the two bottom root 3's to get a positive 3. And then after that, we cancel out the 9 and the 3 to get 3 root 3. All right. Then we can find the value of y. And we're going to use the fact that the hypotenuse is equal to 2 multiplied by the shorter leg. And well, we just found the length of the shorter leg, and we know that the hypotenuse is equal to y. So all we need to do is take 2 and multiply that by 3 root 3. Or in other words, 6 root 3 is going to be equal to y, because all we're going to do is take this 2 and this 3, multiply them together to get 6. We're going to leave the radical alone, and so we're going to get 6 times the square root of 3. All right, I'm going to do another example. This one's going to be using some real life bits to it. So for a second, we're going to draw an equilateral triangle, all right? And I know this is not a right, that's not even a triangle. Let me retry that there. All right. Oops. All right, close enough to a equilateral triangle, don't you think? All right, and this is going to be a yield sign. All right, so if you're driving down the road, I'm sure that plenty of you have seen yield signs before, and yield signs are, in fact, an equilateral triangle. So this road sign is shaped like an equilateral triangle. All right, and we're going to try to find the area of this triangle. And we're only given one side, and that's 36 inches here on top. Because this is an equilateral triangle, we know that each one of these angles are congruent, and those are all going to be 60 degrees. We also know that all three sides are congruent, so those are all going to be 36 inches. All right, so we can break this equilateral triangle in two by go ahead and split it down the middle. So we're going to erase that, and we're going to take this and split it down the center. All right, and when we do that, this is going to intersect perpendicularly. So now we have two right triangles, and they're special right triangles, because if this angle over here is 60 degrees, and this one is 60 degrees, when we split this 60 degrees in half down here, we're going to get a 30-degree angle. So if you split an equilateral triangle in half, you get two 30, 60, 90 congruent right triangles. And so now we can label this longer leg here equal to h. We're going to get rid of this 36 here and split it up between the two. So we're going to have 16 inches on the left, 16 inches on the right. right? And now all we need to do is find h in this case. Oops, I just made a mistake, didn't I? 36 divided by 2 is 18 inches. My bad. All right, but now all we need to do is find the h in this scenario, and then once we get that, we can apply our area formula equals 1/2 the base times the height. So I'm going to go ahead and just look at this left triangle here, so this one right here, and we know that 18 inches is equal to our shorter leg. Our hypotenuse is 36 inches. We don't know the longer leg. And our formula for the longer leg is the following. The longer leg is equal to the shorter leg multiplied by the square root of 3. And so h is equal to 18 times the square root of 3. And now that we have found h, we can plug h into the area of a triangle. So area is equal to 1/2 base times height, and solve for our area. Here's the thing though, we have to remember that our base is going to be this entire length. So we need to combine the 18 inches back together to get 36. And we know that...
Mic off. Mic on.
Sorry, I had to mute there. I was coughing up a storm. And we know that our h, we just found that, of being 18 times the square root of 3. So our area is going to equal 1/2 multiplied by 36 multiplied by 18 multiplied by the square root of 3. All right, and that's going to equal 324 multiplied by the square root of 3. If you want to call it there and say that this is equal to 324 times the square root of 3 inches squared, that's fine. But the book might ask you to round. So we're going to multiply this out. And when you multiply this out, we're going to approximately be 561.18 inches square. All right, so that's how you can break up an equilateral triangle into two 30, 60, 90 right triangles, solve for the height of the equilateral triangle by solving for this longer leg here. And once you do that, plug back in the original area to find the area of the equilateral triangle. All right, I'm going to draw up another example here. We're going to look at a tipping platform. So a tipping platform is used, or is a ramp used to unload trucks. All right, so for example, we can draw our ramp here. Oops. All right, so here would be our ramp. All right, and your truck would sit on here, vroom vroom. We're not going to draw a huge truck. There you go. So there's our truck sitting on the ramp. We're actually going to get rid of him, but I just wanted you to visualize that. Our height of our ramp is going to be right here, and we're going to label that with an H. And the length of our ramp is 80 feet long. All right, and we're going to ask a couple of questions. The first question is, what is H after the ramp is 30 degrees? So when this angle reaches 30 degrees here, what is the length of our, or how high in the air is our ramp? The second piece of information we want to ask is, what is H after the ramp is 45 degrees. All right, I don't know in what universe you'd be unloading a truck at 45 degrees, but here we are. Oops. And so this is not drawn to scale, by the way. Our H is going to be here. And the thing about this ramp is it has to be perpendicular to the ground, right? So both of these triangles are going to be right triangles. The only difference is one is going to have an angle of 30 degrees. The other one's going to have an angle of 45 degrees. So we're going to focus on the 30-degree one first, this one on top. And because this angle is 30 degrees, and this other angle is a right angle, then we must know that our top angle here has a measurement of 60 degrees. So this is in fact a 30-60 degree right triangle. And because of that, we know that we can find the height based off of our formulas. And notice that the height is actually our shorter leg. So the height is the shorter leg. And so we know that the shorter leg multiplied by 2 is equal to the length of the hypotenuse. And now we just solve for the formula. So the shorter leg is going to be equal to h. We're going to multiply that by 2, and that's going to be equal to our hypotenuse of 80. Or in other words, we divide by 2 on both sides to get h is equal to 40 foot. Oops, I'll redraw that circle. Man, I should stick to rectangles. There we go. Now the 45, 45, 90 right triangle is going to be a little different. All right. So we know that the hypotenuse in the 45, 45, 90 is equal to the leg multiplied by the square root of 2. All right, so we need to divide by the square root of 2 on both sides. We have the hypotenuse is equal to 80. The leg is equal to h. We have this root 2. So h is going to be equal to 80 over the square root of 2. All right, and if you just plug that into a calculator, that will approximate out to 56.6 feet.